So, welcome to the first of many lectures by me that you're going to have to watch online. I hope you are ready for that because it is very, very thrilling. I've never done this kind of presentation format before where I will be giving a lecture to you via these remote videos that you have to watch before class. In teaching, it's called a flipped classroom model, where the direct lecture is given prior to class via a non-interactive format, such as a YouTube video. Right? And then we use our class time to focus on activities and doing the work. Where the more traditional format is in class, you do the learning and then you go home and do the work. This idea is it's flipped. Of course, being remote entirely, everything is at home, but hopefully this will save us from having to sit on Zoom and listen to me monotonously talk about some PowerPoint slide. I hate PowerPoint. Ugh. So, today I am going to be talking to you about Unit 1, Lesson 1, the chemistry of life, and more specifically, the wonderful, most beautiful molecule involved with life, and that is water. Right? So everybody knows that you need water to live. All the living things on this planet need water to live. I want you to think about why that is. Okay. Now, obviously, the answer to that question is not if we don't have water, we die. No kidding, obviously. But why is water so important to living things? And that's what we're going to try to address today. Mechanically, why is it so important to living things? Right? And then the overarching idea of why is it that it's water that we are so dependent upon. It could be other things, right? Could be, maybe, I don't know. But it's water. And why is that? Why is it so uniform a need across all living things? That's a bigger question. We'll get back to that later. Right now, I just want to talk about water. So water is a pretty simple molecule. It has three components, right, which are two hydrogens and one oxygen. And that structure, okay, those pieces, the shapes of those pieces, the properties of those pieces are what give water its overarching qualities. Right? And so this is the big theme in this course, where shape or form determines function. Okay? It's universal. It's true across all of existence in this plane that we live in. Okay? And so everything, no matter how big or how small, okay, its function is derived from its form. Okay? So what it does is based on the way it's shaped. It's really actually very, very, very simple. Everything's very simple. Really, really simple stuff. Okay? Sometimes it's hard to see how simple it is because our perspective as humans is a little bit skewed. Okay? Sometimes we can't see the little tiny things because our eyes aren't strong enough to see them. Okay? Sometimes we can't see the really, really, really big things because our brains aren't big enough to comprehend them. But everything is simple once you understand it. Okay? And so we're going to aim to understand water a little bit better. Most of this should be a refresher from Bio 1, which you had 3 years ago. But yeah, I'm going to delve into some of the properties and cool things about water. Good. Okay, so first and foremost, most importantly, during the last section while I was filming, I forgot to plug this microphone in. Okay. So I just had it on my neck to look ridiculous. Okay. So now it's plugged in, and hopefully that helps improve the audio. This will actually function as a good test to see if it actually has any impact. Because if it doesn't have any impact, I'm not going to wear the microphone on my neck. It just looks silly, right? So, moving onward, we're going to talk about the pieces that make up the water, right? The individual elements, the components. And so we know that water is made up of 2 hydrogens and 1 oxygen. So we're going to look at some of the properties of those elements that make up the molecule. And so they have the individual properties that work together, right, to form the emergent properties of water. And emergent properties are properties that come out when the smaller components work together, and they give the larger thing a property that the smaller components don't have on their own. Right? And emergent properties are a huge part of what makes living things living things. So it's an important concept to understand. Okay. So we have hydrogen. It is the smallest of all elements. It's a teeny, teeny, tiny little guy. Okay. It's made up of 1 proton. And so when we look at the elements, they're defined by the amount of protons that they possess. Because you can change the amount of electrons, you can change the amount of neutrons without changing the fundamental nature of that element. And I can add an electron, I can take an electron off, and all it does is change the charge of the element. Okay. I can add a neutron in, I can pluck a neutron out, and all it does is change the atomic mass of that element, which have impacts on the way that the element functions, but it doesn't change the fundamental nature of that element, right? So as long as I have 1 proton, I have a hydrogen. Okay. So it's eeny, beeny, teeny, teeny, tiny thing. Oxygen is a little bit bigger. Okay. Oxygen possesses 8 protons. Happy oxygen has 8 electrons, and then it has some neutrons in there as well to balance it all out. And so the thing about oxygen is that it's sufficiently big that those 8 protons in its nucleus have a strong pull on the world around it. Right? And so it's heavy in the middle. It's heavy enough to impact things around it. But the electron cloud, right, because it only has 8 electrons, doesn't extend too far away from the nucleus. Okay. So this means that the nucleus of that oxygen has a good amount of strength that allows it to impact other elements around it. It kind of attracts the electrons of things that might float by. Right? And so we call this property of being able to attract the electrons of other elements electronegativity. And so oxygen has a high electronegativity, and so it can kind of grab electrons floating around it. Doesn't steal them, doesn't take them away, it just holds on to them for a little bit, and there you go back. All right, oh, that's a cool electron. I like your electron. Here you go. Okay, so that's oxygen. And hydrogen, being this tiny little guy, is really weak. He can't stand up for himself. So that 1 electron that's floating around the hydrogen, okay, gets attracted by the electronegativity of the oxygen. Right? And so when 2 elements form a covalent bond, they're sharing all of their electrons all of the time. Right? They're going woo, woo in their valence clouds. And so when you have this really big electronegative oxygen, it's really selfish, and it takes the electrons most of the time. And then sometimes it's like, okay, you can borrow the electron, give it back. Here you go. No, give it back. Right? And so the oxygen gets this overall negativity about it because electrons are negatively charged. Right? And the hydrogen, in response, gets a relatively small positive charge most of the time. Right? And so when the electrons work their way back around the hydrogen, it's no longer that negative, that positive charge, right? It just goes back to being neutral. But then it goes back over here. And so now I get this slightly positive charged hydrogen. And the electrons are flying around all the time. Okay? And so this charge is always changing, always fluctuating. And that's very, very important for the way that water interacts with other water molecules. Okay? And so this unfair distribution, where I have my two hydrogens with slightly positive charges and my oxygen with a slightly negative charge, is called polarity. And polarity is the most important property that water possesses. So, polarity. So because polarity gives water a negative side and a positive side, that means that each of the individual water molecules will be attracted to one another, where the positive side of one molecule will be attracted to the negative side of the molecule next door. And now, because there are two hydrogens, there are technically two positive regions to the one negative region. And that is important in the way that the hydrogen bonds form. Most importantly, we see that play a huge role in the way that ice forms, right? The shape of ice, the structure of ice, and the properties of ice, which I'll talk about in a little bit. So when we're thinking about water, okay, we think about this stuff, right? Liquid, room temperature water. Okay? It's a fluidy thing. Right? It's a liquid. And now we know the phases of matter go solid, liquid, gas, plasma, right? In an increasing level of energy. And so a solid has the lowest level of energy, where a plasma has the highest level of energy. Right? And liquid is above solid in that energy state. Right? The molecules within the water can float freely amongst themselves. Right? And the reason for that, okay, has to do with polarity. Everything about water has to do with polarity. When the water molecules interact with one another, they form what is called a hydrogen bond. And it's a temporary attraction between the positiveness of that hydrogen and the negativeness of that oxygen. Right? Positives attract negatives, negatives attract positives. They like each other. Okay. Because the individual molecule's state of polarity is fluid, it is constantly changing as the electrons move around. Right? These bonds are constantly being formed and then broken, and formed and then broken, and formed and then broken. Hydrogen bonds are amongst the weakest of all bonds in chemistry. They're very temporary. They're more of an attraction than a bond. And they're just like, I like you, goodbye. I like you, goodbye. I like you, goodbye. And we see that reflected in the larger whole collection, right? So as an individual likes them, they can attach and unattach, and it makes this whole thing very fluid. You cool the water down enough, and those bonds are more likely to stick, right? The water molecules aren't flying around all over the place because they're nice and warm. They get chilly, they lose energy, right? And so now the negative of the oxygen likes the positive of the hydrogen, and it's strong enough in attraction to hold them there. Pop, right? And so this is how we end up getting ice. Okay? But this positive has another positive here, and it's looking for another negative. And so another negative will come here, right? And if you imagine where my hand used to be, right, it leaves this nice gap in between the molecules themselves. So what you get is a big, beautiful crystalline structure. A crystalline structure that has a lot more empty space within it than liquid water has. So when the water molecules are just breaking and bumping, they can bump into each other, they get into each other's space. But when they slow down and they start forming these more concrete attractions, you start seeing these gaps with nice big empty space in them. And as you know, if you take a nice empty space, right, and you put it in water, it floats. Right? And so that's why we get a solid ice that is less dense than the liquid form, which is a rare thing in chemistry. Right? Most of the time, as we progress up the energy levels from solid to liquid to gas to plasma, right, we see a trend in decreasing density because the molecules, as they get more energy, tend to go, ooh, right? Did I say increasing or decreasing? I hope I said decreasing because that's what I meant. But in this case, okay, when I have solid water and I have liquid water, okay, the solid water is actually less dense than the liquid water. So it floats, which is very important for living things because through the course of evolution, right, living things came out of the water, and having floating water, floating ice on top of water, helps give aqueous organisms a safe place to stay in the freezing months. So that's important stuff. So that's it on polarity, I think. So onwards and upwards, we're going to talk about the relationship that water has with heat. Now, I'm sure most of you at this point in time understand what heat actually is, but a quick rundown. Heat is effectively just the effect of the energy within a substance, right? And so the molecules within the substance vibrate really fast if they're hot, or they vibrate slower if they're cold. Right? And so when they're vibrating really fast, they got a lot of energy. Right? If you touch the thing that's vibrating very fast, it gives some of that energy to you. And now our flesh can only handle so much energy without blowing up. Right? And so heat can burn us if it's hot enough because it disrupts the structures, the shapes of our stuffy stuffs that make us up. So heat being a measurement of energy within the molecules of a structure or a substance. So water, due to its ability to form hydrogen bonds, actually has the ability to absorb a high amount of heat without being altered. And so when the water molecules are bouncing around, right, they attach and they bounce and they attach and they bounce, you add a little bit of heat in there, they just move around a little faster. They're still attaching and bouncing and attaching and bouncing. And every time they form a bond, right, that uses up a little bit of that energy. Some of that energy is lost, right, because we're changing the amount of entropy. Right? And so as you add heat, a lot of that heat is distributed and then dispersed through this bond formation and breaking. So water can absorb a lot of heat without changing its own temperature. And that is a property called specific heat. The amount of heat energy that a substance can absorb, right, before it changes temperature. So water has a very high specific heat. And this plays a large role in the way that weather patterns are formed. Okay? So we see different weather in the interior lands where there's no ocean and where we have the ocean. right? And so the water during the day absorbs a lot of the heat from the sun and then can let it off at night, right, without changing too much of its own temperature. So water-specific heat plays a large role in the global existence that we have. On a smaller scale, right, water's ability to absorb that energy plays a role in the way that we, as a biological creature, cool ourselves. Right? And so, if you think of humans or mammals in general, right, we can all sweat, right? And then that water has some of the heat; it evaporates and brings the heat with it, right? Because it's taking the water off us. If you jump in the water and you get out, right, the wind blows on you; it's cold because that water is removing that heat very readily from your body. And again, that all plays back into the hydrogen bonding of water, so that these hydrogen bonds can form using that heat and then disperse it. And then they just go back together and then they disperse. And they go back together and then they disperse. It's no big deal. Whereas if your flesh absorbs that heat, if the proteins absorb that heat, they fall apart. And that's it. They don't just go back together. And so they're impacted, right? And then they have small things. The molecules can fly around faster. They change temperature. Right? And so water has this kind of buffer against temperature change because of its polarity, because of its hydrogen bonding. So, onwards and upwards. On to the next property of water. I'm actually going to combine two of the properties together because they're very similar things. Okay. We have cohesion and adhesion. So cohesion is a substance's ability to stick to itself. Right? And we've already seen water sticking to itself using its hydrogen bonding properties, its polarity stuffs. Right? It sticks to itself. And you can see that. You put a droplet of water on the table, you put another droplet of water on the table, you push them together, they become one big old droplet of water. Right? And then it's all the same big droplet now. Nobody knows the difference. Right? If you had a blue droplet and a red droplet, you push them together, you get yourself a purple droplet. Right? So that's cohesion. Same, makes sense. Right? Prefixes, cohesion, co, together, e, the same. Okay. Now, very similar is adhesion. Adhesion is the ability of a substance to stick to something else. Right? And so we have adhesives like glue and tape, things that stick to other things. Right? I mean, tape will also stick to itself because it's sticky. Right? But like if I stick tape on a wall, it adheres. Right? Adhesion. Okay. So water has adhesive properties with other substances that are also polar. Okay. So other things that have this polar quality of having this slightly different side. Okay. And so one of the easiest ways to see this is with a glass straw, right? Or even a plastic straw. Plastic straw works perfectly well. You stick a straw in the water, right? If you look inside the straw, it will go up a little bit, because the adhesion and the surface tension of the water is enough difference that the water will go up the straw a little bit, right? Because it's sticking to the side of the straw. Right? If you think about like condensation, that's what I was looking for. Condensation on the side of a cold drinking glass, right? That water will stick on the outside of that glass. It came from the air and stuck on the glass, because glass, as we know it, is also polar. It's made of silicone stuff. That's some silicone stuff. And so they're both polar, stick together. Right? And now this bond is not very strong. It's just like the water bonding to the water. It's not a strong bond. So over time you'll see that gravity is enough to drag the condensation down the glass and onto your table and ruin the finish of your nice table. And then your wife is mad at you because you're dumb and you left the wet glass on the table. And she's totally right because it's all your fault. You shouldn't have left the wet glass on the table. That was stupid. Right? So Yeah, adhesion and cohesion. This is really, really important for a lot of biological functions. Right? In us, it plays a role in the way in which our blood moves through our body. Right? It's much more readily evident in trees. Right? All plants, but trees specifically because they're so tall. Trees are really tall. And so the water, right, has to move from the ground up to the tippity top of the tree, but the tree doesn't have any muscles or anything to push the water up. And so part of the water moving up is that capillary action demonstrated in the straw, right, where the adhesion and cohesion stickiness of the water will allow it to stick to the xylem and the phloem, which are basically the arteries and the veins, analogous structures of the plants, and allow the water to move through the tree or the small plants, whatever plant you're talking about. Okay? And so there are other processes involved because, as I said, the tree is really tall. You might actually know that already, that the tree is really tall, and that water has to go really far up. We'll talk about that during one of our labs. I don't want any spoilers, so I'm not going to talk about it now. I'll talk about it later. But the adhesion and the cohesion and the capillary action plays a large role in the way that water or blood can move through the systems of living organisms. So that brings us to our last property of water that I wish to discuss. And I talked about it very, 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 very briefly when I talked about cohesion and adhesion in the tree example. I mentioned surface tension. And surface tension is the amount of pressure it takes to break the plane of a liquid. And so if you're at that place on the top of the water, right, if you drop a rock in, that rock provides enough pressure to break the surface and go in. However, if you were to take a leaf, right, and drop it on top of the water, most of the time that leaf will stay on top of the water. Right? And now that's also because the leaf has high buoyancy and it will float. Okay? A better example would be a paperclip. Right? A paperclip is dense enough that it should sink in water. Right? But if you do it right, you can drop a paperclip on the surface of the water and it will float, even though it has a higher density than water does. Right? So theoretically, it should sink. But it doesn't because water has a relatively high surface tension. Not a super high surface tension, but a relatively high surface tension. Okay? So it takes a fair amount of pressure to break through that top layer. And once it broke through that top layer, it just sinks. Okay? And so the top layer of the water is actually slightly stronger in bonding than the rest of the water. Right? So the connections of the water at the top of the water are the strongest that they are anywhere within the water. The hydrogen bonding is stronger at the top than it is anywhere else. The reason for this is simple. Okay? So the water molecules are looking for their water friends to attach to through adhesion. Right? And everywhere else in the water, there's an equal amount of water molecules around to attach to and be friends with. Right? So water right in the center is no more or less likely to attach to the water right here than it is to the water right here. So it will bounce around. Right? And those bonds are constantly breaking and reforming. Now, if you imagine the very surface of the water, right, that top layer of molecules, okay, underneath it, there's a ton of water that it can be friends with. Okay? Right next door, there's tons of water to be friends with. Okay? But above it, there's no water to be friends with. Right? So there's slightly less opportunity to form those bonds for those molecules that are directly on the top. Right? And so they're more likely to connect with the molecules on either side of them than a molecule below it would be. It has less options, so they connect more readily with the ones next door. It creates a stronger hydrogen bonding experience. So the individual hydrogen bonds are not any stronger than any of the other hydrogen bonds, but they're more likely to reconnect with a neighbor in a vertical plane than they are to connect with a neighbor in a horizontal plane. Flip that around. Horizontal plane, vertical plane. Oh. So they're more likely to connect horizontally. It makes that hydrogen bond overall experience stronger on the surface. So it's harder to move something through the surface than it is to move it through anywhere else in the water. Okay? That's all. And so that's it. That concludes my talk about the properties of water. To sum it up, water is a simple molecule made up of 2 hydrogens and 1 oxygen. The electronegative nature of the oxygen means that the electrons of the molecule spend more time with the oxygen, making that region slightly more negative, and the 2 hydrogens are slightly more positive. This polarity allows water the opportunity to form weak hydrogen bonds with other water molecules and other polar substances, which give water the properties that it has. So we have cohesion, which is water's tendency to stick to itself; adhesion, which is water's tendency to stick to other things; surface tension, which means the top of the water is more strongly bonded than the rest of the water. We have a high specific heat, meaning it's hard to change the temperature of water. You have to put a lot of energy into the water to change its temperature. And we have that fluid bonding, which makes water a liquid at room temperature, and a crystalline structure that allows ice, the solid form of water, to be less dense than the liquid form of water, which is an outlier in the general principles of phasic states. Okay, so yeah, that still leaves us with the overarching question of why is it water that all living things have come to depend on? Why is it water and not some other polar substance? And that's what I'd like you to think about, and I'd like you to leave your answers in the discussion on the Schoology page. Thanks for coming. Hope you enjoyed my kitchen. Have a great day. There's nothing settled here. In my room there's a king-size space, bigger than it used to be. If you want, you can rent that place. Call me an amenity. Even if it's in my dreams. Ooh, it's taking up a fraction of my mind. Ooh, every time I watch you slip inside. Oh, I'm trying. Oh, trying. Not to think about you. No, not to think about you. No, I'm trying. Not to get into you. No, not to get into you. Oh, with my feelings on fire, guess I'm a bad liar.